Cool. So, yeah, well, welcome to the public paper reading group of Morantics. Glad you made it here today. Sorry for the confusion. We have another event going on, which is a little bit bigger than ours, but I see you all made it here today, so it was very glad. Before I introduce our speaker, I'd just like to say a few words about the event. So we host this event every month, and it's really there for two things: for educating people and bringing people together. So yeah, it's really an event to connect and to further your interest in research, hopefully, and to really get up to speed on what is currently happening out there. And while I close the door, I also invite you to stick around and have another drink or so afterwards, and just talk to each other a little bit. And I think that already brings me to introduce Mones, our speaker today. Very glad to have him. He has done a master's in mathematics, I think, and went on to do a PhD also in mathematics from TU Berlin, and has there had touch points, of course, with machine learning, and then started as an applied scientist at Zalando a year ago approximately, and today he'll tell us everything exciting or all things ML about the pricing platform that Zalando currently uses in their production level systems. So very much looking forward to your talk, and I think Mones is also open for questions during the talk, right? So we can make this a little bit interactive if you like, and otherwise I'm sure we also have time at the end for questions.
All right, thank you.
Cool, thank you.
Yeah. So first of all, thanks a lot. So to Alex and also Martin for the opportunity basically to present what we are doing here at Zalando. It's also nice to see that some folks from Zalando, also from my own team, are here. And let's keep this a bit conversational so that it's not too let's say uptight or however you would call it. So as the title says, I'm talking about like our team within pricing platform, and we do demand forecasting. And I will basically talk about three things today. So first of all, what the business objective is. So demand forecasting is a very general term, but I will try to motivate what we are actually doing as a team within the pricing platform and what we're doing there. Then what our challenges are, particularly looking at the data. And then also, of course, talking about the current model that we use on a, let's say, regular basis, week in and every week. And it will be a sort of, I hope, a high-level talk, so that the objective and the motivation behind these models and so on, the model becomes clear. But I cannot go too much into detail into like super data-specific topics due to obvious reasons. Let's say we come from a company. All right. So first of all, before we start, let's introduce our team. So, as I said, the pricing platform currently has around 100 people. So these consist of scientists, product managers, and whatever. And we are part of this whole, let's say, part of the platform. And our team also consists of scientists, of analysts, of software engineers. We have some product managers, related pricing managers, and so on. And the team mission, so also, sorry, before I forget it, Douglas and Johannes are actually here in the room. And so they might also pitch in for questions in case it doesn't touch my project or whatever. Okay, so, and as I said, demand forecasting is a very general topic. So very simple example as a motivation. Let's assume you sell articles like Zalando does with fashion items, and you run out of stock with a popular article, and then you would like to know how much do you need to reorder. Okay, so you cannot just reorder like tons of this article, because then you might end up in an overstock situation. But if you order too little, you might lose some profit that you might get, right? And so it really depends on the business objective that you want to solve in like which kind of forecast you would like to build. And what we do is a bit differently. Our forecast is basically has the objective to do price steering. And so we want to steer prices, and I will tell you, as I said in a moment, how this works. And yeah, so then basically this is the starting point of the talk. So how can forecasting essentially, or in this particular case, demand forecasting, support article pricing? Okay, so question: who ordered something at Zalando at some point? Probably, I guess a sort of majority. Yeah, perfect. So when you're ready, or let's say looked at the website. Let's put it that way. Let's phrase it a bit simpler. Then what you basically see is usually you see some price. Usually you see at least one price. Let's put it that way. So perhaps you see these Nike shoes, and then you see original price is $54.95, and then there is a discounted price, and this is essentially where we come into place. So we are basically part of the pipeline that gives these price recommendations, and particularly discount recommendations. I will talk about this in a moment, and why we are doing this actually. So if you see something like this, people think, then is this intentional? Like why are you kidding me, and so on. So this is not intentional. This is basically then a buggy thing. So it's not that you want to trick the customer into anything. It's just, yeah, these things happen from time to time, and you will see later why something like this can happen just due to the size of let's say data that we have. Okay, so as I already said, let's look at this problem a bit closer. So also internally, we speak about a black price and a red price. Black price is usually the recommended retail price. So something that you cannot really change. Okay, so we don't adapt the black price according to the discount or something like that. Yeah, right. So if you go to, I don't know, to some store and try to buy a computer, then you think, okay, you see a 25% discount, but the original price is so ridiculously high that you think, okay, this has been adapted. So this is not happening. So there are business constraints in place, and also EU regulations that basically tell you, okay, what you can do with the price, and this price is usually set once. And the price that you can influence is basically the discount. So you always have to make clear what the original price was, and then you can influence the discount. And this is where we come in. And before I gave the example of the supply problem, essentially, right? So you have an article that goes out of stock, and you would like to know how many items of the article have to be reordered. But in lots of cases, you don't really reorder article on an in-season basis. So usually many articles are ordered ahead of the season, so much earlier, and then they don't really get replenished. And what you would like to have is to sell them in a profit optimal way, given business constraints and so on. So that most importantly, you don't have an overstock situation at the end of the season. You also don't want to sell articles too quickly. So because, I mean, then you also might lose some profit, but you would like to, roughly speaking, you would like to sell them in a, let's say, smooth way, so that they are then out of stock at the end of the season when new items are introduced, and so that you are not stuck with an overstock situation, because that's also something that is costly for the company. And so what algorithmic pricing in this case is about, and this is essentially what I've summarized on here. So on an article level, you would like to regularly steer discounts in a profit optimal way, such that severe over or understock situations are avoided. And this is the important point, the global business constraints are fulfilled. So you can, of course, discount every single article independently, but then you don't know what happens on a big scale. And of course, you have some business constraints that the company gives you, essentially. So let's assume you have something in market, whatever. Market means country or whatever, and you say, okay, I want to make that much revenue in this country, stuff like that. So that's a big optimization problem. And what we basically do is to try to solve this optimization problem. Okay, so and now I will tell you how a forecast comes into place. So this graphic here, basically it says agent environment. So this is basically formulated a bit in the context of reinforcement learning. We don't use a reinforcement learning approach, but you can just interpret it in such a way, essentially. And let's start with what you first see. So let's go the other way around. So you go to the website, as I said, you see some prices that are displayed in the shop. And then people start to buy stuff, right? And so you can collect essentially trading data. So you see, okay, what I have my articles, I have certain countries, I have dates. I can basically just collect, okay, people buy that much of an article for this day in this week or whatever. So okay. And then what you then end up with a large bunch of training data. And this training data can basically then help you to forecast. And the forecasting, and in this particular case, we are most interested in demand forecast, but of course also other forecasts are relevant. So you would like also to know what the stock estimate is, return rate, and so on. So all of these then basically give you an idea about how much of the article would be bought in the future. And if you know for certain discount levels how much of an article is demanded in the future, then you can try to steer the discounts accordingly. Okay, so you sort of have unobserved demand. Okay, so that comes out of the forecasting system, and then using this unobserved demand, you try to steer discounts in a let's say profit optimal way given these constraints. And this is a big pipeline, many people are involved, but what we are essentially doing, most importantly, is this demand forecasting model. Any questions or anything up to this point? Yes.
So when you do the forecasting, do you also consider other items that might be linked to it? For example, I don't know, look at a bikini or something and someone buys the top, and then obviously you can then estimate that the bottom should also be bought.
Not explicitly. I will say this later, so we don't do this explicitly. You can try to analyze your forecast and then come up with patterns, but this is sort of an already very good point because it's a sort of open direction that you try to model these article interactions more explicitly. Yeah.
And the constraints that you're dealing with from business side, are they country specific or?
It depends. That they are it's a bunch of constraints. They can be country specific. They can be what can it be? So country specific, I think are the most ones. But what else? Category specific. Okay.
But maybe country specific.
So categories means then.
So you optimize, that's the most important part. Advanced, it looks like you can spend a certain amount of discount on a given country, basically, or investment if you want.
Yeah. So so you also have constraints in place that you don't give too high discounts, for instance. So that this is like something, and then you try to calculate some sort of average discount rate or whatever.
Yeah, and that constraint would then come from the country itself, from pricing manager or something.
Yeah. So these are externally set.
Yeah. Okay.
This is essentially what our neighboring team does, and they consume our demand forecast essentially. So as I said, here the key point is essentially that we forecast for different discount levels, and this is what I meant before. But if you want to look at the demand forecast, you should basically adapt it to the business at need. And so the question basically is then how many items, like to put it very, very high level, how many items of article X, so we do this on an article level, for every article we try to forecast this, would be bought in country Y, so country means market or whatever, in the next Z weeks. Z, I will also tell you basically, this is basically, we do a forecast that's for the next 26 weeks usually, if we would give D% discount. And the D then is basically a variable of the model that you can try to adapt, but I will tell you a bit later. All right. Okay, before we start with the concrete model and how it looks like, let us first talk about the data itself, because this is quite a challenge in itself to build a model for this. Because first of all, we have 2.8 million articles, roughly speaking. So we have a history for 2.8 million articles that are expressed as time series with different covariates. So you don't have, you can sales, you have stock, you have discounts, you have categorical features, like, yeah, the category of the article, if it's for which gender it's there and so on. And also very important, we have messy data sources. And so the data that we use at the moment is also already error prone because we have to aggregate at some point. Very simple example, if you look at sales, then every sale is actually recorded somewhere. And you somehow have to aggregate this to an article level. And also the article level, I will also talk about this a bit later because we don't only look at every single item, but even on an aggregated level, but this I will touch upon a bit later. And then what we have is a distribution of demand, which is not very favorable. So we have, so here in this graph, you can see the demand plotted against its frequency on a log scale. And what you can essentially see is that we have lots of zero sellers or low sellers, let's say. And then fewer and fewer high sellers, but these high sellers, this can be a very high number. I think I'm not allowed to share, but yeah. And then, like, coming from this problem, you can also then basically look at a single article. So this is what we have here below. So here in this, sorry, you cannot see my mouse pointer. Okay, it doesn't matter. So in the time series below, essentially, you have a single article, and so what's plotted there is essentially the ground truth demand, how it develops essentially, the discount, where you can basically see in the middle that you get a spike when the discount is essentially higher. So the yellow part is the discount, and then also what our forecast does with it, and you can see this also quite often this example. And problem here, so we have essentially three major problems that can all be summarized in this one picture. So first of all, if an article gets introduced, and this happens every season, then we have a cold start problem, right? So we probably immediately see some sort of demand after the article has been introduced, but how do you want to do forecasting with this, right? So if you just use a forecaster, separately for every article, then you couldn't capture this. So this would then be basically referred to as a local model, right? So you have a separate forecast for every article, or you use what we then do, a global model. A global model meaning that you forecast basically at the same time for all articles. Then short histories. An article gets introduced, it gets sold, goes in and out of stock, and at some point it vanishes again because the next item is introduced. And this is why this question about like grouping similar articles together becomes important again, because you might gain some knowledge from an article that is not that far off from a newly introduced article, but just 1 year later, essentially. And then we have sparse time series. So meaning what you can see here, basically, we see some spikes, but then also lots of zeros. Can be weeks where we don't sell anything, right? So, and then suddenly we see a quick jump in popularity and whatever. Okay, second problem, and this is a big one because we do a demand forecast, but you should not. You have to distinguish between sales and demand, because demand is only sales if you don't have stock constraints. If you're out of stock, you don't really know a priori what the demand is. And this also touches our ground truth, right? So it's not just a forecasting problem that we're dealing with, but also about our past data, because our past data, in our past data points, we don't know what the exact demand is if we had stockouts. And this is a bit depicted here in this graph, where you can see, okay, demand is always lower bounded by the sales, but it could be that we are in some week where we suddenly see a spike in demand, but we don't observe it. Okay, and so there are essentially two for any forecasting model where you want to deal with this kind of data. You need to somehow deal with it. Either you leave it out and you let the model somehow try to learn what the future demand will be, and you mark these data points as missing or whatever. Or you use an explicit sales to demand extrapolation, right? So you try to explicitly model what demand is by observing sales and from the history of an article or whatever. And this is what we are currently doing. And I will also tell you on the next slide a bit more in detail how this extrapolation logic in the current state looks like. But it's also work in progress. So this is what I'm, for instance, working on to overwork this together with some other team members to overhaul this logic because it's faulty. Okay, and so this is basically then the other difficulty. So as I already said, we have these levels of aggregation. First one, we have a weekly resolution instead of a daily, hourly resolution or whatever. So we do a forecast on a weekly basis. Every week, we essentially upload a new demand forecast which is then used in order to give discount recommendations. And for this, we have to aggregate. Right? And this is not so much a problem if we do it for sales, for instance. So sales, we can easily aggregate by just summing them up. But if you want to aggregate discounts, this is not an entirely trivial task, although we solve it rather trivially at the moment. Just taking some sort of average. And this means that you don't capture inter-week spikes in discounts, for instance, right? It can be that you have a recommendation set by some, let's say, pricing managers or whatever, that for a certain limited period of time within a week, you will see a high discount and then it drops again. And so you cannot really model these kinds of things. And what other team members basically are currently working on is to build a daily forecast so that you are closer to how sales events usually happen. And the big one is, for instance, Cyber Week, or you all know this from Zalando or Amazon or whatever, so end of November. And so you try to somehow model this on a bit more granular level. And then the second one is that we use an aggregation on a size level. So we group all sizes of an article together. So if you look at the sizes, then on the website, then you see basically this list. And yeah, we treat all of these equally. And why? It gives us potentially less noisy data and also much less data, because the problem is these 2.8 million articles that I talked about, this is already on an aggregated level. So, and on average, every article has 4 to 5 sizes or so. So if you multiply that, then the problem becomes much harder and even noisier. But what we do is essentially we use this logic. We use this aggregation in order to use the extrapolation, in order to provide the extrapolation from sales to demand. And what we do here is essentially we try to leverage demand by looking at the past distribution of the sizes. Okay, so some sizes are, of course, more popular and some sizes are less popular. And then you can observe this in weeks where the article has been fully available for all sizes. And what you essentially do, we assume that we see we have these 3 sizes, S, M, and XXL. And you observe sales, and you know in these cases that sales is equal to demand because these sales have been these sizes have been fully available for the week, and then you essentially infer the demand by looking at the historical size distribution. This is roughly what's done, but this logic has some flaws, and yeah, it's currently work in progress to overhaul this, or don't use it at all, or whatever. Any questions? Okay, so these are basically some difficulties that we have, and now what I've been talking about is actually what kind of model we are using, just to give you an idea, how we train it, how long that takes, and so on, and then also talking about the limitations of this model. So one was already mentioned, that we don't explicitly model this article interaction. Okay, and this model, so basically the one here in the middle, I will show you on the next slide, but this essentially consumes historic data. this, if you remember from one of the first slides, we essentially put everything into the model that we can get our hands on, and there's still stuff missing. Because even if you work at Zalando, it's not always easy to get the data sets that you need, so due to compliance reasons and so on. And what we can basically get our hands on is essentially you have this, you have historic demand. Let's say you take the last year. This is a time series and for 14 countries. So we do forecasting essentially for 14 countries at the moment. Let's say the biggest markets. These are country dependent. Then we have country independent time series, meaning these are global, or so they have just one number attached to them and they are not specific to countries. For instance, stock is not treated to be country specific. So generally you just use the overall stock because you can essentially ship it anywhere. We have categorical features such as the brand or something called commodity groups. And then this is basically the past data, and what we want to get is essentially the future demand for 26 weeks for 14 countries and different discount levels. And so what we essentially do here is we put into the model these future discounts that we want to forecast for. This is trained on the full Zalando article assortment because we want to use as much history as possible. And basically we put in time series that have a length of 1 year. But we go back up until 4 years essentially. And so this is then basically what our model sees in training. And then we forecast future demand based on future discount. Okay, just very high level. And now this is basically the part that has not been resolved yet. So what we do here is essentially we use a special transformer architecture. So something that you know from, of course, now it's in the news, let's say much less sophisticated version of what you know from ChatGPT or whatever. So it's essentially based on the same ideas as in the original intentions from the paper. So we have an attention mechanism here. And we have the model inputs that are basically tensorized. They are embedded, not all of them, but many of them are embedded. And then we have an encoder and then a decoder. So similar to what you have basically in a standard transformer. And basically this part here, so these two parts on the right, these are the ones that are distinguishing themselves essentially from what a current transformer has, or sorry, what a standard natural language processing transformer has. First of all, we have two decoders. So we are mostly interested in the so-called near future. So let's say we want to predict for the next 5 weeks or whatever, and this is where we have the most focus on. And we train this separately from the so-called far future decoder, which looks at then, I think, the weeks from 6 to 20 or whatever. So for the next weeks in advance, and this is also for computational reasons, so that it's not that you don't explode computing costs, let's say, too much, but also because we don't really care necessarily about what happens in the far future. It should not be completely off because our optimizer somehow, so the optimizer of our neighboring team somehow relies on it. In total, we have then roughly, I don't know, 5 million. The number fluctuates a bit, but between 5 and 6 million parameters that the model basically needs to be trained on. Yes?
So you say you make forecast for the next 26 weeks. Can you say on what resolution? So
weekly. Yeah. Everything's on a weekly resolution. So you put in time series on a weekly level, and then you forecast for weekly on a weekly level. Yes?
And so I am not completely sure. Is this like a single model that is predicting all the outputs, all of the Zalando articles ever that is in the database, or is it applied per item? So the same model is applied per item and giving a single prediction for a single item.
Yes, so the model is global. So you can basically, depends on the items that you have, but you can put in any number of items here, and then you get for any item you get the output basically. So it's we use the same parameters essentially for every item. So yeah, in this sense, it's not trained separately for every time series.
Why are not all of the inputs embedded? I think that would usually be useful in transformers to map common representation space.
And some of them are already like what we do is with some of the features we log transform them. And this is basically then all of the embedding that we do. Why we don't embed everything probably has been tried out in the past.
There's a lot of trying error, yeah.
So I think like you try to find what sort of works best, and then if you have something like discounts which are always anywhere between 0 and 1, then you don't do the hustle and encode them in a different way. So mostly the categorical features, most importantly, are embedded here.
Are they all handcrafted?
What do you mean?
Or are they
Just standard, I would say. Like yeah.
not learned also?
No, it's learned. It's learned, but they are not. There's no fancy architecture behind it.
Features itself are not result of a statistical model. They are just passed from the data. Apart from the demand, if you wish, because demand is like an exploration.
I mean, we do some data mangling, as I said, right? The discounts are also a bit handcrafted since we do this sort of averaging, but not on a large scale. So the demand is the biggest, let's say, not pain point, but the biggest thing here. So the biggest extrapolation, let's say.
What is near future and far future, and how do you select them?
Yeah, it's like the near future is the one that actually interests us, or the optimizer, let's say. The optimizer of the neighboring team is interested more in the near future. Near future means the next 5 weeks or so. I will show you a bit later also. And the far future means you look a bit further and you don't want to be completely off in the far future. But I mean, you can also only test this like half a year later then. But you have to provide the optimizer with values basically for the next half year. Why? I don't know. Maybe because the motivation was that 26 weeks correspond to one season or whatever. Yeah. Okay, so then the second part, which is, let's say, handcrafted in this sense, is the generator layer. So the generator layer then provides us with a model output. And we don't, per time series, we don't project just one single number, but we want to project 26 weeks times countries times discount levels. And the discount levels we choose is basically, we do a very simple linear interpolation here. So this is something that can certainly be challenged or substituted at some point in the future, but we forecast essentially for discount level 0, 0.1, 0.2, 0.3, up to 0.7, so 70% discount, and then essentially output the forecasted demand here. And this is, as I said, a piecewise linear output layer. And so the question is, what should this sort of fulfill? We don't want demand to be negative, right? So it should be 0 or above. It should be monotonically increasing with respect to the discount, meaning this is our intuition, right? So if I give a higher discount, then the sales should go up if I have enough stock. It's a time dependent, so-called base demand. Base demand in this sense means basically the anchor that you have at 0% discount. So this changes, of course, over weeks. Summer jacket will sell less in winter than during summer. And then the one thing that we enforce here is essentially that we have a similar shape across the time dimension. And similar shape in this case means monotonically linearly increasing piecewise linear function that is monotonically increasing. That's a model choice. Could think of other modeling choices that you have something smoother. You can try to get motivations here from economics theory or whatever about how demand behaves with regards to discounts or prices. All right, and then if you look at it from another angle, essentially what we also do is we forecast, as I said, for 14 countries. So what we had here before is we forecast for, in this case, 10 weeks. But this is just for one country. And here I basically look from another angle. I have 1 week, but I forecast for 14 countries. And this is essentially then how the model output will look like. So we have a dimension here of 7 times 14 countries times 26 weeks. Okay, any questions? This is rather simple, but can be challenged very easily. Yes.
Someone in the chat asked, like, how long is the time horizon you look in the history for your training data set?
Yeah, so the slices that we put into the model are 1 year, but we look back for 4 years. Okay, so then we have a basically sliding window. Yeah.
How do you validate it in a way that you don't confuse the temporal, so you don't inject look-ahead bias? So do you checkpoint the model that you are training? So up until this point?
Yes. So first of all, in the training we perform masking so that the model, so that we don't have information leakage essentially.
But don't you?
The evaluation. So we do this on a week-by-week basis. And so we can only tell at least 1 week later how well we were for the first week. So it's always like in the so if we train it, let's say training starts on Monday, it uses last week's observations. These are the latest ones, let's say. And then you look back for 4 years, and then you try to forecast for this week. You don't want to go back in time. Essentially, you want to go forward in time. And then in the end, you can say after another week or after another 26 weeks how far off you were.
Do you train a single model then, or like a model for each fold that you?
Not a single model. It's a single model.
So, and then the single model is trained in a way that you're respecting the temporal nature of the folds. So, yeah, that's correct. Okay.
All right. Yeah.
Is the model trained from scratch, or do you initialize this with previously trained models?
It's usually trained from scratch. And but Johannes did some analysis in the past. What would happen if you take an older model, and how fast the degradation in our, let's say, KPIs is. And you can some. So if I got this wrong, then please interrupt. But I think you can up to a point use an older model and don't have a massive degradation in KPIs. But this might get worse over time. There's also in this paper that I've linked at the end, there is a graphic that visualizes this phenomenon. And now a bit more technical, how do we train the model? Essentially, for training, and this is also something that can be challenged, we use something different for training and for evaluation. The training is essentially an approximate true loss. We have the main distinctions here, as I said, the features are log transformed, so the demand is log transformed. And in order to stabilize training, you don't use the exponential function in the end, but Taylor expansion and cut it off at a lower order polynomial. And then what we do is, as I said, we train for 7 epochs for the so-called near future. So for the next 5 weeks, I showed you the decoder split before into the near future, far future. And so you first train for 7 epochs in the near future, and you can see basically here roughly how the train loss behaves. And then in the end, it will spike again, because then you train 1 epoch for the far future. And as I said, this far future is just sort of a sanity check, because we have to provide these numbers. But they just shouldn't be too far off. And what you usually see at the beginning of the epoch is essentially a drop, and then it sort of levels off. The evaluation of the model is a bit differently. So here we take the business value into account. And so what we basically sum over is, we sum over everything that we can get our hands on. So basically the black price, so the non-discounted price. Also here, why the non-discounted price and not the discounted price. And then you basically, so that's a question you could ask. And then you essentially measure this sort of normalized black price weighted relative L2 error. And on the other hand, the bias. Okay, so this is very, let's say, specific, I would say. And yeah, you can compare this. There's some correlation with how the RMSE, for instance, behaves. So it's not completely off. There's just this black price weighting. And what does the black price weighting tell us? This means that more expensive articles are penalized heavily. Okay, so if you are off here and the article is more expensive, then you have a stronger penalization. Yes.
Why aren't you running this in a multitask training setup where you would mix near future and far future samples essentially? So why are you training first near future and then far future?
Because of computational considerations, I would say, because I think that was the original motivation here, because it's quite costly to have these prediction windows of also 26 weeks in the model.
So part of the model, I think, correct me if I'm wrong, the encoders, the weights are used from the near future, and then the updated model using the far future. So there's a bit of optimization. So if you run it for the whole time frame, it becomes very costly.
Okay, yeah, thanks.
Yeah, this is basically about the forecast evaluation itself. And this you can do, as I said, like you train your model in the week that is under consideration, then at least 1 week later, you can see how well the model performed essentially. And what you can also do is essentially you can try to evaluate the effect of the forecast on the downstream task, because that might be different. So the evaluation here might lead to a different result to what the forecast performance itself tells us, because what we are actually interested in the end is how well did our forecast behave if we look at these discount recommendations, and then you try to basically leverage on what you actually observe. So you have the actually materialized stock, you have the actually materialized returns, the actually materialized sales, and so on, and you try to put everything together and then try to evaluate it. All right, so then last thing about the model itself. So the approach, as I said, in general can be challenged, because there is some literature that tells, okay, transformers might not be the best thing to do for time series forecasting, and they might also be a bit overkill, as deep learning models in general are, because trees perform well in these competitions and so on. So what we did is essentially to do a bit of benchmarking on these closed data sets. And what we did here is we didn't train this on the, so a colleague of mine did this, we didn't do this on the full data set, but on a small part, smaller part of the assortment, and try to basically get some, without doing proper, let's say, so this with a disclaimer, without doing proper feature engineering and so on, compare this with other models that are out there. So LightGBM is a tree-based model. DeepAR is a deep autoregressive model coming from AWS, so Amazon Web Services. And then we also have a naive forecaster, just as a benchmark. So naive forecaster means you just take last week's observation and repeat this essentially. And what you can see is, okay, the naive forecaster is not terribly off. And this is something that you often observe with regards to time series, that simple models can get you a long way. But then to get the extra mile, basically you need something more complicated. And down below, we basically provided something that is called a scaling laws. Probably heard of them, or maybe heard of them in the context of natural language processing, where there is a paper by Google, I think, the original paper, where they say, okay, transformers behave very well with regards to several parameters, one of which is the set of the training, the size of the training set. What we have depicted here is how does the forecast performance essentially behave if we increase the size of the training set while keeping the test set constant. So we just take 700,000 articles to test on, and then we just increase the number of articles that we train on. And you can see that that the amount of articles, and this is another point that we are, let's say, lucky to have at Zalando, because we have this many data points, lead to a boost in performance if we just increase the size and then train on this. what you can see, these intersections is essentially when does the model perform better than the naive forecaster. So the one where you just essentially repeat last week's observation. And so this is on a log scale. So you can see, okay, after at most, I think 6 or 7% of all data points, you will in these simple cases always outperform the naive forecaster. All right. Then just very quickly, because I mean, this is not data science related, but since talking about forecasting at scale, how do we orchestrate stuff? And this is, as I said, part of a bigger pipeline that in total takes roughly 2.5 days. And depending on the GPU instance that you take, the training itself takes in the current setup 2 days. I mean, if you take a more costly instance, then you can reduce this, of course. And yeah, the pipeline relies on different technologies. So the data is usually stored in S3, so Amazon S3 buckets. And then we use Spark, we use SageMaker, Kubernetes. This particularly the light blue thing might be a bit overkill, let's say. Something can be reworked, and then we do the monitoring. And the monitoring means what I said before. In retrospect, we try to measure how well your model actually performed. And what you basically do is you just look at an historical average, and then you observe whether your forecast performance is significantly worse than what it used to be in the last X weeks, let's say. And of course, there are some signals that might indicate that your forecast performance will be worse. For instance, you have a sales event that is not captured properly in historic data. Sorry. So what we don't have, for instance, is a flag for sales events as a feature in the current implementation. So this is something that the model might miss, and then you have to somehow identify what happens. All right. Challenges with the approach. First of all, it's a point forecast, right? So we don't provide for these discount levels confidence intervals. We just provide a single number. Something that should be reworked at some point. Then it could be that the true discount to demand curve is not necessarily monotonically increasing because of other factors that confound the picture. So there could be something that you have something that you're missing, why this might not be the case. Then what we discussed before, interactions between articles are not explicitly modeled. So the model is a global model, so you have weight sharing, but you don't specifically know how the forecast for one article influences the forecast of another article. Then we don't explicitly model also hierarchical relationships. And this is also a bit similar to what you've asked, right? I mean, you can group items together, either by category or maybe by similarity of time series or whatever, and then try to leverage what the demand is, and using techniques from hierarchical forecasting that you have that you provide a forecast on a higher level and then try to basically split this up somehow that you also get a forecast on the lower level. Then, I mean, for the business itself, it's not too important. Rather, you would just want to see a trend, but the forecast accuracy will deteriorate for a long forecast horizon. So this is something that we regularly observe. You can see it here basically on the right. As the relative week essentially progresses, our error goes further up. And what I've already mentioned, the weekly resolution is not suitable for short-term discount jumps, right? Because if you take an average and your discount stays the same for 6 days, but then it just has a spike on the 7th day, this averaging will not capture this. And as I already said, like colleagues of mine are working at the moment on a daily resolution. Then you can go broad here and say, okay, well, this is one approach, but can we also go a bit, let's say, crazy and do more elaborate adaptations of the model? The first thing is we provide this demand grid for several discounts, which we basically set. right? So 0, 0.1, and so on. And then in retrospect, you can actually evaluate for the actually materialized discounts how your model performed there. But this is of course just one point, right? So let's assume in the end the article gets 15% discount. You can just only evaluate your model there. But of course, these discounts are not set randomly, and there's some generating process that you might want to take into account in order to basically or which you would like to try to model in order to get a better understanding about how prices are set. And this is what's the fancy word is like causal inference, that you try to account for confounding factors of this price mechanism. We get this correctly. And so this is what basically Douglas and Johannes are working on. Then what I've already said, but this is also a bigger topic, that you move away from this point forecast into a probabilistic forecast, that you provide confidence intervals for your predictions. Multivariate forecasting, again, article interaction. Does a discount for a high discount on some article kill other articles, for instance, or does it boost sales for similar items or whatever? Then what we also don't do is to explicitly model the environment that we are in. Right? So, I mean, we have competitors, and these competitors set discounts. These competitors have similar or even the same articles, and so on. And this is a big task to achieve. So, I mean, you can what you can do is try to scrap. I mean, this is what another team is doing, that you scrap other web pages and try to basically find matching products and then see, okay, what is the discount given there and so on. And this also, but this is a much bigger explosion basically that you will witness. Then if you get this part right, essentially, then you're maybe on a good path to do reinforcement learning with reinforcement learning techniques if you get the environment sort of right. But this I mean, this is a very big open topic, just like to mention here. And with that, I'd like to conclude and thank you for your attention. And as I said, like, you can find this the recent article on which describes this approach in a bit more detail. Thanks.